Hello. Can the speaker online speakers hear me?
Yes.
Okay, thanks. There are others. I guess we can start. So hello everyone. So welcome to this tutorial at CordsComat. So this tutorial is on a very interesting topic: the promoting sustainable water usage and management with water data, AI and policy. So I am Shaptarshi Ghosh from IIT Kharagpur. I am chairing this session, and I would welcome the presenters of the tutorial. Bihu from IIT Roorkee, who is present here in person, and Biplav Srivastav, Harish Prabhat Gupta, and Manavendra Saharia. So Biplav is from University of South Carolina, Hari Prabhat Gupta from IIT BHU, and Manavendra Saharia from IIT Delhi. So welcome to the speakers online as well. So without more further delay, I'll hand over the mic to Bihu for starting the tutorial. Thank you.
Good afternoon, everyone. Thank you for being here today. I don't see a very large crowd here, but thank you to all of you who have joined in online. Today, we are going to talk about promoting sustainable water use and management through AI. And I will be joined in by my colleagues, Professor Hari Prabhat Gupta from IIT BHU, Professor Manubendra Saharia from IIT Delhi, and Professor Biplav Srivastav from University of South Carolina. Uh, so today we are going to talk about a couple of things, and before we get started, first I think we need to talk about water, the general landscape, the ecosystem, the framework or the paradigm within which we conduct all these conversations. Then we, of course, we have to jump into where AI can step in and provide solutions, whether it's providing short term solutions like whether this body of water that I see in front of me is fit for swimming or not. It may be an easy decision like that, or it might be something a little bit more complicated in terms of how do I ensure climate resilient operation in my water and wastewater systems. So it can be something short term, it can be something long term, it can be a simple decision, it can be something slightly more complicated. But at the end of the day, AI has a very large role to play in these decisions, and we are going to talk about some of that. We are, of course, going to illustrate some case studies which, through our work, we have come across, and we are going to discuss the details of those. And also, we would like to end our discussion with certain research questions that we are working on at the moment, questions that we would appreciate, help or support or inputs from the audience, and of course, leave it up for collaborations and further discussions. There are four broad topics that we are going to talk about today. So like I said, first of all, we are going to talk about water and where in this entire landscape does AI set in, or what are some of the fundamentals that we need to know before we move forward. So that's one of the things. Of course, we also need to understand water data, what exists, what does not exist, what do we need in order to move forward. AI solutions, where do they come in, what do they do, how could we improve upon them, and so on. And then we would like to end with your inputs or your thoughts, or leave it up to you to think about what it is that you could do next, or what it is we could do together, in terms of the next steps. So let's start our discussion about water. And this figure here probably take you back to your to your school days, where we learned about the water cycle. We learned that precipitation comes in as either rain and or snow, depending on where in the earth you live on. But that the water that comes in from that, if it if it is exposed, if the surface of the water body is exposed to the atmosphere, we usually call it surface water. If it is found under the ground, we call it groundwater. And then through evaporation or evaporation and transpiration, which we call evapotranspiration, this water once again goes back into the atmosphere, and then this cycle continues. So this is the part of the water cycle which we generally refer to as the hydrological cycle, which is the natural part of the water cycle, and that is something that more or less we are quite familiar with. The other area, the other cycle that we very often look at is the urban water cycle, which mainly looks at water consumption. So what do we look at within the urban water cycle? So there is a body of water. It may be surface water or groundwater, like I just mentioned. So the water may come from the surface of the earth or may come from under the ground. That's really not the important question here. But what is more important is that we are taking that water, we are treating it to a certain degree, making it fit for drinking, and then we are supplying it to the customer or the consumer here. And then after the consumer or the customer has used up this water, then it becomes what we refer to as sewage or wastewater. And that once again, through a network of pipelines, is transported to the sewage treatment plant or the wastewater treatment plant. And here a lot of treatment takes place, and then we break down the pollutants that we find in water, and we make that water fit to be discharged back into surface water bodies or groundwater bodies. Now, this is typically what the urban water cycle looks like. However, there are modifications to this, in the sense that we are now talking about, we are talking about potable reuse, which means that at the wastewater treatment plant, we try and treat the water to a certain degree so that it becomes fit to drink right from here. So, if any of you have been following the news, Bill Gates has been a major proponent of making potable, making wastewater treated up to potable standards. And there's a very famous picture of him drinking a glass of water which he took out from a wastewater treatment plant. So there are a lot of psychological barriers in the acceptance of water that from a wastewater treatment plant in terms of drinking. However, we are working towards those, and very soon, out of compulsion or for some other reason, we might have to adopt potable water, potable reused water into our day-to-day lifestyle. Now, what wastewater treatment plants are considered to be a very significant part of what we call closing the loop. Or in other words, when we talk about this cycle, what makes it a cycle is that the wastewater treatment plant, it treats the water and sends it back to the water bodies. So that way we can envision this as a cycle, which is a very important part of recharging and renewing our water resources. Now, when we look at regulations, so quality regulations come into at two places. So the quality of the water that you're drinking, and the quality of the wastewater that you're discharging into the water bodies. So these are two important parts where we have regulations that come in. And then finally, we have been talking a lot about saving water, reducing our water usage. So the way we do that is usually we try to reduce distribution losses, which means that when we are supplying the water from the drinking water treatment plant to the consumer, the distribution system that we have, we try to reduce losses there. We try to install water saving fixtures in each and every household. We try to improve mindful water use, make sure that a consumer does not waste water. And finally, we try to improve sewage treatment. So these are some of the ways in which we typically look at this problem. Now, if you have not been living under a rock, you might know that there is a water crisis that the world is facing in various degrees, right? So, why is it a crisis? Why is it a problem? So, the broad reason why it is a problem is that there's a huge difference between supply and demand. What that means is that we know that of all the water that we find on earth, a large part of it is mostly sea water, and a very small part of it is fresh water. And if you break that down further, you will see that most of it once again is in the form of groundwater, or in some way it is water that is not directly usable by us. Not to say groundwater is not directly usable, but I think in terms of extraction, it's a slightly more complicated process than extracting surface water. And the surface water in itself, a very small part of it is found in lakes and rivers. So this is the supply situation that we have. If we look at demand, what we see is that a large part of the water demand comes from agriculture, and unfortunately most of the water that is used up in agriculture is what we call consumptive use of abstracted water, meaning that this portion of the water is now not readily usable by other stakeholders. So the idea we are trying to motivate through this particular slide is that there is a short supply and there is a huge demand, and there is an increasingly growing demand, mainly because of our lifestyle. So these are a couple of quick facts on how much water it takes to produce the things that we use in our day to day lives. So for example, if you're drinking a cup of coffee, then you are probably using 140 liters of water in the process. Now that might seem a little bit strange at first, but the entire process of growing coffee and processing it and treating it and bringing it to your table would require about 140 liters. So similarly, if you're wearing a pair of jeans, you are probably using somewhere around 10,855 liters of water for just one pair of jeans. There are similar statistics about a cotton t-shirt, which is about 2,700 liters. So you can see that the water use is not just what you use out of the tap or how much you drink, but it is also, there is a lot of inbuilt water use in the products that we use every day, or the products that we consume every day. So that is also an important thing to keep in mind. Now the water stress that we are facing across the world, that's not something new. That's not that we all know about it. We also know about the day zero situation at Johannesburg, and a lot of cities are expected to face similar circumstances very soon. If you consider this graph or this image, where between 1995 and 2025, you will probably notice that US, which was not a major groundwater user, has now shifted to groundwater use in a very large way, and now it's about 20 to 40% of the total available water. So the idea here is that it's not just developing countries like India which will face water stress, but a large part of it would be faced by developed countries also. And so this is not just a regional issue or a local issue or a national issue, it's very much a global issue as well. Why do we have these challenges? Because like I said, there is a huge mismatch between the demand and the supply, but also because we do not have proper management practices in place. There are hardly science based or science driven ideas which will help us in better management of our water resources, and in better management of the gap between demand and supply. um, So, if you are, partially familiar with the water landscape, or if you have been following it for a couple of years now, you would probably know that a lot of the, water decision making was not data driven, or when it was data driven, it was based on data sets that have been collected manually. And, it's quite easy to predict from that that these data sets are not very exhaustive. They can only capture the performance of a system at a very short period of time, and it's just like a small window in time, and we have focused our decision making capabilities on these small data sets that we have tried to manage problems in isolation, or in other words, we do not have an integrated thinking. This is what we typically refer to as a siloed approach in water. We are only looking at drinking water, we are only looking at wastewater, we are only looking at surface water or groundwater, hardly looking at things in conjunction, or looking at things as a unit or as a system. There are multiple data sets existing in different places, and there were no efforts to integrate them. And as a result of these, there are a lot of issues that follow with building a model, trying to understand system, trying to predict system performance, and so on. Now, the movement, and this is partly led by the role of AI, is now towards a different kind of a future, where we have we have access to sensing equipment, we have access to larger databases. So how do we manage them? How do we make sure that this data helps us in predicting performance, helps us in making better decisions, and so on? So we are now moving from this old mentality, so to speak, of towards a new age, which will be better guided by data obtained from sensors and various AI techniques applied to those data sets. So like I was just mentioning right now, that there is this typical siloed approach towards water use, where we only think about drinking water use or only wastewater use, and hardly about integrating it. So there is this new term that's widely being talked among the community, which is what we refer to as integrated water resource management, or IWRM. So in IWRM, we look at water as one resource, and we look at all systems together as much as possible to try and understand the path of water, mostly through the urban water cycle. So it's no longer looking at systems in isolation, but trying to integrate them and trying to understand their impacts in totality. So as I mentioned in while I was talking about the urban water cycle, is that wastewater treatment is considered to be a very key component of circular approaches in water use, which means that we are trying to close the loop, or we are trying to send back water into our surface water or groundwater systems through the use of wastewater treatment, or through judicious wastewater treatment. Now the one of the things, we always keep talking about climate change, we keep hearing about climate change in the news, and there are very definitive impacts of climate change on our water resources, definitely also on wastewater treatment. And that is something that I try to do through my work, through AI based models. We try to understand how climate systems impact wastewater treatment systems. And since I am from Roorkee, which is in Uttarakhand, a Himalayan state of India, we have the problem of flash floods, and we have the problem of cloud bursts in the upper reaches of the state. So that brings the question that, we have a lot of small wastewater treatment plants. So those are called decentralized systems. We have a lot of these decentralized systems in the vulnerable parts of the state. So whenever a flash flood happens, how does it impact not just the quantity of the water that is coming into the treatment plants, but also the quality of the water? And this is an important question, because with climate change, we have kind of established that these kinds of extreme events will keep on happening. So how do we build climate resilient operations into our systems? So these are some of the results that we've just generated from an analysis that we've been doing. And let me just set the stage for you first. So in India, what we have, the wastewater that is being generated from the households is taken to the treatment plant through a set of pipelines, which are referred to as the sewer lines, right? There is a separate and dedicated system of pipelines that takes water, the rainwater that we receive, which is typically referred to as storm water. It takes that water, and it either takes it to the wastewater treatment plant, or it takes it to some surface water body, depending on where you are. Now these are two very different or separate pipelines that we have. And ideally, the assumption is that, or the design assumptions, even when we are designing these pipelines, what we take into consideration is the fact that if there is a rainfall event, the stormwater sewers will carry it. And if you have regular wastewater that's being generated out of homes, that will be carried on through a different systems. However, because of climate change, and because of these short spikes of rainfall that we've been having, meaning that, very short durations of very intense rainfall that we've been experiencing again and again in various parts of the country, we are now experiencing or we are now witnessing a unique phenomenon, wherein the storm water is now making its way into the separate sewer system. So you must have seen this around you. Whenever there is water logging in a place, they will generally open the manholes, and they will allow the water to drain in through the manholes. But what are we doing there? We are accessing the sewer system, the regular sewer system that we have, and we are letting we are letting storm water into that. And this is not something that the system is designed for. more importantly, the wastewater treatment plant that is at the end of this pipeline or this network is not designed for that. So now we are bringing in unexpected stormwater loads into the wastewater treatment plant as a result of that. So this is kind of the problem that we were trying to look at. And this graph that I have here on the left, um, so this graph here, the line in in red here, that shows you the influent flow into the wastewater treatment plant, and the line in blue here shows us the precipitation levels. So what I would like to point out from this particular figure is that whenever you have a short period of very high intensity rainfall, so these spikes in the blue line, you would probably see a spike in the influent wastewater quantity as well. And so that just goes to support the assumption that I was trying to make, or the point that I was trying to create when I was motivating the problem, is that this storm water is now making its way into the wastewater treatment plant. And remember, the wastewater treatment plant has not been designed to handle these kinds of loads. So this is something unexpected that's happening, and it may overwhelm the wastewater treatment plant, or in certain cases it may create what we refer to as washout, which means that the plant does no treatment at all. So it has completely failed. So in extreme situations, that might happen as well. So just to see what this dependence looks like, we have seen that temperature, when temperatures are less than about 20 degrees Celsius, which is typically the winter temperatures for Roorkee. So whenever there is rainfall during the winter months, we have whenever there is rainfall exceeding about 13 millimeters in winter, we have a very high inflow coming into the plant. And just to keep things in perspective, so 2720 is about 2.7 mld, or 2.7 million liters of wastewater coming in, and the plant is designed only for 3. So we are very close to the design limit that the plant has been set at. So it means that we are very close to the situation where the plant is completely overwhelmed by the wastewater that's coming in. So this is just one small example of a use of regression tree, which is, as you all of you would know, is a popular machine learning technique, where we understand these kinds of relationships, where we see how precipitation, and not just precipitation, but precipitation during which season, which we have identified to be the winter precipitation, how that leads to a situation where you have where you overwhelm your wastewater treatment system. So these kinds of patterns, or these kinds of relationships, or these kinds of dependencies emerge very well through the use of AI or machine learning. So now, to give you a perspective of what's happening all around the world, water management is probably in one of the more rudimentary stages in India. I would say we are making strides, but we need to quicken our pace, so to speak. So to give you an idea of what's going on in the US has a lot of very consolidated databases which have been, and the data collection process has been going on for quite a while now. So one of these data sets is available at the ECHO website, which stands for Enforcement, Compliance and History Online. Here you will find a lot of different data sets from across the country related to air quality, wastewater quality, bio solids, and so on. So you will also find a very nice GIS based portal where you can find a visual representation of the locations where these data sets have been collected from, and then the time series of each of these data sets. An interesting example also comes from UK, where you can see the link here on your screen. But what this tool does is that, once again, it's a GIS based visualization tool which helps you understand which is the nearest location around you where you can go for swimming or bathing, and what is the quality of the water in that particular point. So that is a very quick and useful tool for people who want to go and spend a day swimming, and whether the location nearest to them is safe or not, or if they maybe have to drive down a couple of kilometers to get to a good spot. um, Another example is from New South Wales in Australia, where they have a similar, once again, web based tool. But what this does is, instead of water quality, it gives us a idea of the quantity of water that's flowing through each of the tributaries in the particular river. And of course, you can understand that there might be flood warnings and things associated with that, so you can keep a tab on what is the water level in the river at any given time. Another very good data set comes from USGS, and like I was talking about, consolidated databases where data has been collected for a significant period of time over several locations, is what we call USGS, so US Geological Survey. If you go to their website, you are going to find a lot of information on stream flow, water quality, and data. Going back to several years. So they have had stations which they have maintained all across the US for quite a period of time, and they have been regularly uploading the data sets there. So if you're looking for good data sets to work on, these might be some of the places that you hit. Another initiative also comes from wastewater treatment or sewage treatment, is from Spain, where they optimized the process strain of a wastewater treatment plant by using dynamic data. So like I said, we conventionally have this habit of thinking um, in snapshots of data that are available, or we look at these small windows in time. But there is a lot of wealth, or there are a lot of insights to be gained from dynamic data. And through this particular analysis, they were able to demonstrate that if you look at dynamic data, you not only get huge reductions in electricity consumption, but you also get better treatment overall, and you also get sludge quantity reduction. So these are some of the interesting examples that have come up from different places across the world, and also just a very small insight into what it is that I do, what kind of work I like to do, and how I like to blend AI into the work, into the water work that I do. So now I am going to pass on the baton to my colleague, Professor Hariprabhat Gupta, who will be talking about water data and what his team has been working on.
Yes, thank you very much, Professor Bihu.
Stop sharing the screen.
Yeah, can you please? Yes, now I can share. Yes, so very good afternoon to everyone. I am Hari Prabhat, and here we start on water data. So, in this session, we try to cover up what is going on in this direction, in this project, and what we have done. And here, we main focus on that sensory data, how we can collect the sensory data, what we can do, and the final results. So, this is the title of a project, Water to Cloud, where the objective is to build systems which is the sensor networks for water bodies for collection of the data and process it, display it. So water to cloud in this is a project title. So this project is to initial to map water quality over the large bodies using the cyber physical system. So that's where we are using the word of water to cloud, collect the water data, put it on the cloud with the help of the cyber physical system. And this is the data size is very big. So the features that we can say that okay, what is the uniqueness in this? So this the data size is very big. That means they have the 1,000 data points in the 3 hours over the 10 square kilometer of water bodies, and here we covers almost all the Indian rivers. So the point is that one whatever the we have seen that the data is from outside the India, some US European is rivers and water bodies data is there, but on this side, on this portal, we collected the data which is especially for the Indian rivers, and the data set is there. Number second is that uniqueness is data is visualized. That means the heat map sort of thing. So very easily we can identify that whether the pollution is level, what is the pollution level, what is the heat map. All this information is visualized not in a tabular format. And of course, this is open source, so can freely download, freely available for the machine learning, deep learning, or the futuristic process. Now we come to the process, how we build this data set or what process we follow. So one thing is that first we identify some locations and hire some board and attach the sensor on the board. Boards are moving inside the water bodies here and there. We use the sensor props to collect the sensory data, record it, and download this data, clear the data pre-processing, upload on the portal. So basically the three main steps that we follow in this entire process. And before that, what is the motivation for water to cloud? So we can see that around, especially in India, that 14 billion liter of the sewage is every day, and it affected the 70% of the surface water. However, what cannot be fixed, the lack of the data points. It is costly, promise, limited scope, and no source. So all these points keep in mind that okay, these type of the problems are already there, but because of these issues are there and the solution is not exist. That's where this W2C comes into the picture. And entire information is about the W2C, their data set, their application, and other things are available on that portal. So now we come to the what rivers or what water bodies that is the data set is available. So right now that is the 14 bodies are there, 9 is this and other is the 7. So especially that since ITBSU that Ganga River is the wake of this one, so mainly we focus on the collection of the data waters or pollution or the sensory data of the Ganga River, which is in the nearby the Varanasi region. So here, but with the help of these systems, we have the 14 rivers and also some lakes are there. Total 14 bodies are there. So Bangalore lakes are covered, and entire heat maps and everything is available on all these 14 bodies of the water. And this is the complete six pictures, six steps that we follow, and details are given. So first thing, a very important thing is identify the site of the interest for monitoring. So say for example, in the Varanasi, the holy city, so numbers of ghats are there, people are coming for bathing for their own religious purpose. So find out the hot points where we can measure the pollution level, and this pollution level measures or give the information of the entire region sort of things. So identify the site is the first point. Then after once we fix the site of the point, if we measure the pollution level at this point, we can easily measure the pollution level of the nearby point, or without measuring we can predict the pollution level. The second one is that of course to hire the arrange the boat, attach the sensor on this one. And the third one is the moving the boat 10 to 15 kilometer route maps, and we try to make this route map fixed so that in the next day when we collect the data, we collect the same route map so that we can compare the previous day and the current day pollution level. Then execute all these regular body data collection and the template, and using the data filtering and other things download, and finally the data is available. So this process we repeat for all the 14 water bodies and now, while collecting the data, when we use the data set word, there are two categories collection is there in this project work. One is the sensory data, where we fix the sensors with the board for collecting of the sensory data. Other one is the laboratory data. We collect the water sample and send to the lab identify the pollution with different perimeters values, and once again give the result. So there are two things are there. One is the sensory data, other one is the laboratory data that we have collected. Yeah, of course, the collection of the sensory data and see the measurement is very fast and also the low cost as compared to collect the lab data, send to the lab, collect the results. All these things is the time consuming and also a costly process. So in the sensory data, first identify the location, then after sensor placement in the board, then after data acquisition, collect the data, pre-processing, and of course data transfer and storage comes into the picture. Now, what sensory data that we have collected? So these are the some general data: the DO, pH level, turbidity, EC, temperature, and These thermal, these are the some standard sensory data that we have collected all these, and once the collection is done, then such type of the heat maps comes into the picture. So say for example, DO level is the entire this region. When the boat move from this to this is almost similar, and that is very high. pH level is the different region. Even this is the river, same river at the same time we have collected, but the different of the pH level. So indicates that okay, which one is the high, where is the high, and analysis purpose. That is, an entire data set is available. Now we go to the lab data, collect the data on the site, then after send to the laboratory, do the pre-processing and storage. So here the unique thing is that if you collect the sensory data, we are not able to find out some parameter which is only possible with the help of the laboratory data. Say for example, federal level FC is there, BOD is there. So these parameters we can easily find out only with the help of the laboratories data. Now it indicates that the sensory data is not enough sufficient to do all these exercise. So laboratory data is also required in that case. These are some graphs or some results that okay, what is the data points and how the changes are happening with the these perimeter, what are the perimeters that we have considered. Now we comes to where AI ML comes into the picture in this case. So as we already seen in the previous slide that the sensory data, they measure some sensor units, and the lab data they also measure some water pollution level units. Now the problem is that lab data takes time. Lab data is the costly collection and all these things. So we try to use the AI ML to sort out these issues, whether we have no such that parameters, how we can find out the water quality index with the help of the sensory data. Even sensory data is the limited. So the exercise what we have done, collect the sensory lab data, water pollution lab data, then after sensory data, using some models and find out the results. So here these are some steps that okay, perimeters, how we can select the perimeter, perimeter tuning, and establish the weight of it, because the water quality index is a different in different scenarios, or as well as different countries. So every country they have the different water quality index and their perimeter. So we need to give the weightage of the water quality index for different data. So here we can see that the picture there. So say for example, dissolved oxygen, NSA follows the perimeter 70% weightage of the dissolved oxygen when we estimate the water quality index. But since we have no such complete data, all these perimeter data in the sensory data, so what we have done, we can convert like this one so that we can find out the almost same result water quality index with the help of this mapping or with the help of this arrangement. So water quality index indicates that if the index is between 80 to 100, what we have estimated that is the excellent water, the sixth level. And if lie between 0 to 30, then that is a very poor water and nothing to useful. So with the help of this exercise, we can estimate what is the water quality index, and based on that one, we can identify the levels that which one level 1 to 6. If the level is 1, the water is very polluted, and the level is 6, water is good. And these are some deep learning models that we have built for collection and identify all these things. Now, if we measure the W water quality index with the help of sensory data, with the help of lab data, then how to share this information to the end users? Because, say for example, in the Varanasi, various tourist comes into the picture and they identify which ghat is less polluted and which ghat is suitable for their bathing purpose. So they want to measure the water quality index. They want to see the water quality index. So here we use the complete IoT concept to do all these exercise, collect the sensor data, identify the water quality index, and use some communication protocol to share this information to the end user. However, for making the balance between the load of the users and the data sample, that game theory comes into the picture so that they can balance between two parties. And this is the IIT BSU region where the lab is there to measure water quality index. And this is the sensors where we can deploy the sensors and the board they collect the data. And for communication purpose, we use here the LoRaWAN communication protocol, which is the less energy consumption and long range communication. So the age of these nodes are so far so that they can collect the data periodically and transmit continuously. And now, if the users is with the help of APIs, if they connected with the lab data, they can real time they can measure the water quality index of these different points. Now, this is their choice that they can select. Okay, this is the less polluted, then they can go in this guard or that one guard, that guard. So this is the real-time water quality index measurement and the sharing of that water. And this is some sort of the machine learning and deep learning model that we have used for estimation of water quality index. Then we use the game theory to make the balance between the user utility and the sample collection, so that we can make the balance, load balancing, and generate the result sort of thing. So this is the another architecture of the water quality index for how to measure, how to transmit this information to the end user. So in this presentation, we try to build a complete that, okay, how to measure the water quality index, then transmit, then sharing with the help of sensory data, or with the help of lab data in that case. So thank you very much from my side. Now my request to the Professor Manav, please continue. Thank you.
Hi. Can you continue sharing your slides? I can just speak off from your slides. It's not allowing me to share.
Sure, I'll speak that thing.
Yeah.
Yeah.
Hari, if you want, I. Oh, okay.
I think we are on 51. Yeah. Okay. All right. So, good afternoon, everyone. So, I'll be talking about some of the citizen science and applications that we have been working on at IIT Delhi, and where we look at alternative sources of gathering natural disaster data. So, we have a project called Indra, which is the International National Natural Disaster Research and Analytics. And it's basically a suite of tools that we have developed or are developing in order to collect a large volume of natural disaster reports. So even though on the slide it says flooding reports, but we are actually collecting a lot of other information as well. So the idea is that we will combine the active and passive crowdsourcing. So active crowdsourcing are mobile applications, messenger bots, wearables, web forms, and so on and so forth, which requires a user to take action to provide us data. And passive crowdsourcing is when we do social media parsing and then even IoT based, LoRa based uh, tools where we are collecting data, but we don't really require user input. And we have developed a central API that processes all the data into a single format. And then on top of that, we have data cleaning, geospatial, converting it into geospatial data formats that are amenable for web as well as desktop applications, because that is what ultimately it is used by most government agencies. And finally, interfacing with different socioeconomic data sets. And the idea is to finally develop real-time dashboards. Next slide, please. So this is just the home slide of the application that we have developed. It's deployed in Android Play Store right now. So if you go and Google Indra or Indra Reporter, then you will find it there. And in the home screen, you can see options for rain, flood level, flood impact, landslide, visibility, earthquake, storms, and I think lightning storms. So the idea is that people will be able. So we have made a couple of things here to optimize the information that we get from people. For example, you are not allowed to change the geolocation, which limits the ability for someone to report data from elsewhere. But it also means that the information we get is has greater accuracy or at least trustworthiness. So we collect information on various disaster types, primarily I'm interested in looking at flooding and storms, but we have kept other options in case other researchers want to use the data. So the idea is that all user options are within 3 clicks, because in a fast moving environment where you're experiencing a natural disaster, you want the UI to be as smooth as possible in terms of getting data, or if people want to see the dashboard, whether it's a it's a zone that is experiencing some problems. So the user interface is minimalistic. So we collect user locations and report times in our online database. And the API, we have kept it free. You can access it from any interface, apps, bots, chat interface, exactly, etc. And the idea is that we can that common people in developing countries, especially in India, are able to use it and give us flooding data set. A similar project is actually ongoing in US under the National Weather Service, where they are able to collect more than 200,000 reports a month. It's called MPing by NOAA, and we hope to replicate a similar work here. And but our because NOAA is limited to meteorological phenomena, so ours is more like surface phenomena and natural disasters. Next slide, please. So this is just one of the workflows that I'm showing. It's if you click the flood level, for example, how can we take quantitative information from ordinary people who may not, non-specialists basically, who may not understand the difference between 1 and say 1.2 meters. So we allow them to visually give us the data. So the lady and the tree that you see, everything is like visually marked. So the lady is kept like 6 feet and the tree is like 12 feet. So so you can move the slider up and down and give us data of water levels that you're experiencing. And all of this is ultimately very useful for validation, because it is extremely rare to have this level of granular information when it comes to flooding. Even from satellites, you don't really get flooding information, you basically get inundation. So this kind of information is very useful for flood modeling. And finally, we have a dashboard already set up in indra.iitd.ac.in if you want to look at it. But there is a lot of work that needs to be done in terms of making it even better. Next slide, please. So this is another one of those workflows where in the first screen, if you click the flood level, if you click flooding, it will take you to the second screen, which allows you to take the level and report the flood level. And in the third screen, which is the final screen, it allows people to associate an impact with it. So every flood is on 5 scales. It's four scales actually: minor, moderate, major, and severe. And all of these is it kind of agrees with the internationally accepted norms. So we have kept the workflow in a way that the data that we generate, we can actually use it with other data sets around the world. Next slide, please. So all of these applications are built using React Native because we want to take advantage of, we want to reduce the amount of work that is required to make multi-platform applications. The API is developed using Django REST framework, so and the data set is stored in a Postgres SQL database. And the strength is that we have kept it open source. The data set is freely available, so if anybody wants the access to the data set, I'm happy to provide it. Next slide, please. So currently, we have also developed a Telegram app, because most people nowadays, they don't really want to download a app, especially a special purpose app, because this is not really a shopping or anything that you'll be using regularly. So we also have a Telegram chatbot that you basically replicate the same workflow there. And we have found out that a lot of people by a lot of people, I mean a couple of dozen at this moment, because it's quite new, have started giving us data on different rain and storm events, which are going to be useful for evaluating hazard information in the future. So this pilot study is being done it's open. The data set is being collected across the world, like anywhere anyone can provide, but the pilot study is being done over Delhi. And we are attempting to translate it to major languages, but right now it's only in English. Next slide, please. And this is a second work that we are doing, where we are looking at an IoT-based real-time water quality monitoring system, similar to what Professor Hari had already presented. And we had a couple of nodes we had a couple of sensors that we had set up at a lake nearby IIT Delhi, where we were looking at more intense measurements over Hari's work is more on the river scale, but this one is more intense on a lake scale, like in a smaller area basically, but we are trying to see even within a lake what is the variability of water quality. And we have deployed the sensor, and we have put it on the ThinkSpeak network and displayed it, and we recently published a paper on this one. And so this is some of the work that is ongoing. The idea is that we can use a lot of new tools to generate new data sets. Right now in India, in water resource, in natural disasters, flooding data set is that comes mostly from Central Water Commission. And those data sets are at point locations where they have sensors. So we need alternative ways of gathering data sets, and that will really help us to develop better models. So that is the purpose of this work. I think that is my final slide. Okay, thank you very much.
Thank you, Manav. Um, Hari, can you unshare so that I get a permission to share? Yeah, thank you. Okay. You should be able to see my screen. Yes.
Yes, yes.
Thank you. So what I will do next is I will talk about how the data can, and AI techniques can be used for meaningful insights to common people. So here is a quick summary of what do we mean by AI, and you can think of the field as on the left hand side by the goals that they're trying to pursue. Are they trying to build intelligent systems? Are they trying to understand human brain? They're trying to understand mimicking human behavior and so on, as just a data science and so on. And you can also think of AI by disciplines, whether it is by learning, representation, reasoning, decision support, multi-agent system, trust, and so on. Okay. I wanted to put this because next slide, I want to talk about the whole range of possibilities we have with water data and what we can actually offer. One way to think about this is that we can think of the stakeholder whom we are trying to benefit and what are they doing today, what data they need, and how we can actually provide them better insights. So, for example, if it is an IT organization which is putting out sensors, and we can help them find out missing data and outlier detection and things like that. For individuals, they might be concerned about where can I take a bath, what crop should I grow if it's a farmer, and so on. Okay. And then if you're a policy maker or a farmer, you want to see figure out which crops should I be promoting to grow in a particular region and things like that. So depending on the stakeholder we are looking at, the use case, there are different kinds of data and different kinds of techniques from a whole range of AI areas which are possible. So in this section, I will focus on three use cases which we have worked on. The first one is on tourism management using water data. So, what to do during Kumbh Mela, for example. This is a work which I was involved with around 2015 to 2017 timeframe, and using a platform called Blue Water, which we developed while I was at IBM Research. And then I'll talk about inspection of polluting industries, how to figure out good ways of inspecting uh, polluting units. And this work we did around 2017 timeframe. And finally, I will talk about a decision support with water quality data. This is a chatbot which can help people, guide people based on what activity they are interested in. And this is ongoing work we are doing both in India and the US. So, just to recap, we talked about three broad categories of data collection. We talked about taking samples and doing lab testing and so on. It's a quantitative approach, and it is time consuming and costly. We can also do real time sensing using various sensors. Not everything can be done using real time sensors, it is quantitative. And the science here is how do you deploy your sensors and analyze data. The another category is crowdsourcing, where apart from you can actually get qualitative information, like people can take photographs and give information. And in India, with a lot of people and a lot of mobiles, that's also a practical way. And then you can also combine qualitative and quantitative data here. Okay. So, in the particular work that we talked about, the variation comes in the kind of sensors we are using. So, we used a particular sensor which had these parameters that it could measure. So, I'm not going to go into the detail of that. We also had developed a crowdsourcing platform to get water data, which is called Neerbandhu, Water Friend. And we had mapped out information in the Ganges data, in the Ganges Valley. And that's some of the information that you see. So again, this was around the 2015 to 2017 timeframe. Okay. And then based on the particular activity, you could see what the water parameters are. So I will not go into the details of the blue water, but go directly into the actual use case and the AI methods. So the first method I'm going to talk about is trying to assess tourism impact using water data. Okay, so if you know about Kumbh Mela, this is something which happens in different places around the country at different times. The specific work we talked about was the Haridwar Earth Kumbh, which was around 2016. And here, one of our partners was IIT Roorkee. So, as you know, any kumbh or earth kumbh, there are different dates, and then you have different baths or snans on different occasions. So, people converge on different snan dates. During this earth kumbh, about 100 million people actually came. So, what we want to ask is how much does the human activity impact water quality? And where is the impact highest? Of what kind? And in fact, we can even use this to estimate how many people have come to these bath places. Okay. So, again, so in this particular case, the kind of usage we were interested in was drinking, bathing, and irrigation. Irrigation of the crops is something which is regardless of the particular activity, but drinking and bathing is could be because people are coming there. Okay. So, over a 76-kilometer stretch of the Ganga, we actually collected different kinds of information on using the physical sensor and also through the Neerbandhu app. Okay, so this is what is being shown out here. So you can, of course, map it out based on individual parameters, like we talked about turbidity or dissolved oxygen and so on. That's what we are actually showing. But what is interesting is we are also seeing it on major bath days or not on bath days, so you can see the impact based on people. But what we can also do is this figure actually is a little involved. What you have is different dates on here on the y-axis, and on the x-axis we are showing the conditions based on various water parameters. So it is not mentioned here, but for example, this is pH, this is conductivity, and so on. Eventually, we are combining them together on a water quality index. So we know the red is a bad water, is the worsened water, and the greener is a better water. Okay. Now we can also do this to cluster the water quality. And this is useful because if you know a little bit about how the snans are done in Haridwar, there is one ghat where most of the one side where most of the bathing is happening, and there is another side where not the bathing is happening. Okay, so based on water and on the peak snan days, you can actually see that most of the water the impact is actually on one of the ghats. So water is telling us a story about human activity, and this is something which we can verify, and this can be used by people who are doing crowd control, even for people who are businesses who can do various activities around major tourism events. Okay, so more detail about this particular way, what we actually did is in the associated papers, but I just wanted to mention that water data tells us a story, and AI methods can actually help us in getting to that story. In this specific example, the AI methods were used in data cleaning, normalization, handling of missing values, in combining qualitative and quantitative data, of course, in the clustering, and then we can actually use this in explaining and assessing validating various assessments. Then the second category of the second use case I want to talk about is inspection of polluting units. So this is the work which I was involved with University of South Carolina, sorry, University of Southern California, with the Milind Tambe's group. So, as you know, tanneries are they actually process leather, and they create various leather products. They also discharge a lot of water, and with various kinds of pollutants. So they are. This is old data, around 2016-17 data. At that time, it was about $1 billion of revenue they were generating, and 100,000 people they were employing. The problem is that when the pollution in water is too high, uh, the government does a knee-jerk reaction. Let's close all the tanneries. Okay, that is actually a failure of the fact that there were procedures, there are people who can inspect, and yet our inspection regimes have not been effective. That's why we have to do these knee-jerk reactions. So, this is a slide just telling you where what is the process of leather processing and where water is actually discharged. A whole bunch of water is discharged during chrome tanning, and the tanning steps, like the chrome tanning, which is out here, which I'm pointing out. So the problem here is that the specific, depending on the unit and where it is discharging water, chromes, sulfides, suspended solids, and COD, these are some of the important parameters to be watching out for. And then, depending on whether someone is discharging directly to the river or to a sewage treatment plant, they need to be further monitored. So chrome is the most important heavy metal which actually needs to be monitored, and it was 45 milligram per liter, where it should have been less than 1 milligram per liter. So it's hundreds and thousands of times more than the permissible limit. Okay. So in this kind of a setup, what we do is we actually frame this into a game theoretic problem. We suppose there is an inspection office, and there is a river out here. There are multiple tanneries which are shown out here, and the tanneries at a particular location, they are together into what is called a site. So you have multiple sites. The setup is such that these sites, when if the inspectors actually visit a site, everyone knows that inspection is happening. So although the inspectors will only visit one of the tanneries, everyone else will shut down their water discharge, chromium water discharge. So you cannot actually visit everyone. It is enough to just attack or visit one of the sites. So the attackers here are the inspectors. Okay. And uh, the attackers are the M sites and the factories, and which you want to visit. The defenders are the inspectors, and they consist of inspectors and security team and transportation people. And the idea is, how do you form teams and how do you come up with a regime for inspection, so that you actually improve your probability of finding violations. Okay. So with this setup, we actually have a more detail on what the input and what the output is. So the output is an inspection plan and then inspection schedule, which will maximize your probability of success. And this work we actually had, it's a simulation based work, and we got some validation from experts in the field on this. So the AI methods here is as you would imagine, how do you actually solve the game theoretic problem? It's a Stackelberg security game, and how do you actually define come up with the mechanism design? The last category of use case I want to talk about is decision support to common people based on a dialogue interface. So when we actually have a major water problem, we give out water advisories. In the US, uh, after we had issues with water quality coming from the lead, sorry, water coming from the tap in Flint. This was due to lead and copper. EPA came out with the advisories on the website that you can do something, you cannot do something. Okay, and near the river, near the water bodies, you always have signs like uh, do not actually take a bath here, or there are some issues. There is algal bloom which is out now, so don't do something. So, given these advisories, which are static, non interactive, non contextual, and they don't actually take the data into account, the question is, can we actually create decision support tools, which is the hallmark of AI systems, and can we provide contextual data driven information to people which they will actually follow? Okay. So with that, we actually built one of those systems, and I'm going to give a quick demo of this. This is a YouTube video which I'm going to play.
Water Advisor is a chat-based tool for exploring large amounts of water quality data using machine learning techniques. Here we see a map of the United States. The blue dots indicate locations where the current prototype has data: Flint, Michigan, and New York State. First, let's investigate Flint. Let's look at Flint, Michigan. Now we can take a closer look at the data for Flint. I'm interested in drinking water quality, so I'll ask, where is it safe to drink? The map is now color-coded based on drinking water quality. Red locations are unsafe, and green locations are safe. On the left, we also see regulations that bear on water quality. We can click on the dots to get more detail. Here we see detail for 714 Spellman Drive. We can see it's unsafe to drink. At the left, regulations that contribute to this assessment are highlighted. We can also see pollutant levels for this location. Let's look at bathing. Is it safe to bathe? The map is now color-coded based on water quality for bathing. Here is a location where it's safe to bathe. Notice that different regulations are highlighted as supporting evidence for this assessment. Now let's look at data for New York. I want to drink in New York State. We now see water quality sensors spanning New York State.
So I would like to just summarize here that what you saw. You saw a chat interface where you could type or you could talk. There is a map interface where you could point and get more information. There is an evidence tab where you could look at the regulations at different granularities and for different pollutants. So it was at the EPA, which is at the federal level, then at the state level, which was for Michigan, for example. And when you actually pointed at a particular location and asked for why, you could actually see the regulation. So this is like an explanation tab or an evidence tab. Okay. So such kind of interactive systems is what we believe is very useful, because technical information like pH and BOD and so on, they are useful to technical people, but they are not much use for common people. So how can we make a meaningful abstraction and provide insights to end users? That is the key problem we are looking at. In the current demo, which I mentioned, we are using data from US Geological Survey, which actually gets data from surface water 6 to 7 times a day for about 2,000 sites across the US, but only for a very few parameters out here, like conductance and temperature and dissolved oxygen. And there's a lot of missing data. So in this particular kind of approach, what we are doing is we are asking a question. We are looking at the water pollution data. It is if the pollutant is quantitative. There is also information about the regulation, and we want to know the region and the purpose. So, for example, a state or a location and the purpose, whether it was bathing or drinking and so on. The question is of the kind, can I do a purpose at a location? And this kind of a structured querying, we actually are mapping to the data sets, and we are actually mapping back to the regulation, and we are reasoning on the quantitative and qualitative information to actually give an answer like yes, no, or uncertain, along with an explanation. So the quality of the AI or the sophistication of the AI increases the more the abstraction and the more it can handle imprecise data. Okay, and just to kind of mention that drinking water is not just a few parameters. There are about 45 parameters based on WHO different mandates, and we can find some details even on Wikipedia. So answering these questions, even when you in the presence of missing data or missing parameters, how do you do that? So there is a whole area on in reasoning in AI which can handle this qualitative and missing data. So this we can actually do by assuming that the water is safe by default, and then any information which can help us figure out that the water is unsafe, right? So it is background knowledge. We are assuming that it is safe, and we need evidence for unsafety. Okay, so that's how we can actually tackle the lack of missing data and yet make meaningful interpretation. Um, so we have this data, and then there was a site which we actually provide on GitHub. In JSON, we provide the regulations in at the state level and at the federal level, which we can actually map out, and we can use it for answering the questions. Now, this GitHub is the where the regulation information is actually put in JSON format. This is another form of AI where we are trying to understand the regulations. So there are various data needs, and we need to understand the activities like bathing, drinking, fishing. I mentioned about the GitHub, where the regulation information is actually and the mapping to the activities is given. So you can actually check this out. We have regulations from India, New York, Michigan, and EPA. There are some more enhancements which are coming up, and we have used water quality data from USGS. And in terms of the AI methods, we used constraints, rule-based processing, preferences, and knowledge graph. Okay. And just to kind of give you an appreciation of the complexity while trying to solve this problem, regulations, they can be at the international level, country level, or regional level. There can be something which is specified at the international level, but not at your country level or at your state level. Okay. So, but with this kind of information, we can actually benefit from regulations at any other place. So, within even US, microplastic regulations regarding microplastic is not provided for any other state but New York. So if you are in a state like South Carolina or California, you're trying to ask this question, although the regulation is not applicable for that location, you can benefit from the fact that some other jurisdiction has developed it. And if you want to be aggressive about your water quality, you can actually benefit from regulations from other regions. Okay. So without this, without further going into the detail, I want to focus on a couple of problems that we are focusing on right now. The first one is AI-guided tool to identify false reporting of water quality data. This is something which Bihu and others are actually quite interested in. The idea is that a lot of data is actually reported. Can we actually validate it? And what methods can we use to validate it? Okay. The second problem is, can we actually issue alerts based on water quality data which people will follow? So today, first, even if we know that the water is bad and it's not unfit for people, we don't issue alerts. And even if we issue alerts, people are not willing to to take it up. So how do we generate alerts that people are going to follow? Okay. And so to that, it is actually a multidisciplinary approach, and we are trying to tackle that uh, with people in water, in AI, and in communication, which is in journalism. So we are looking at how do you actually generate it and also evaluate it using communication principles. Okay. So I want to actually so with this, we are coming to the end part of our tutorial, where we are going to just sum up quickly that we have introduced the water ecosystem. We have also summarized the research problems of current interest that we have been working on. And I think we have talked about two of these focus problems, and we welcome any new areas that the community wants to actually bring up. There are some resources we have actually provided, like the data standards. We also have information on some of the ongoing resources that we actually referred to in our tutorial today. This is some of the references in the Blue Water resources. And I would like to end by talking about a couple of slides about AI research issues. One of them is on sensing, which is about deciding whether sensors to use, how to sense cost effectively, how to involve people as sensors, okay, which is what the crowdsourcing work was about. Then interconnection, when you have data from multiple sources, how do you actually combine them? And then can you use it across different domains? Then last but not the least is analytics. How do you actually make all of this available to people in a decision support setup, like as a chatbot? And how do you actually price to incentivize water conservation and the behavior change of people? That is what you actually need towards the end. So with this, I will like to stop and open up for any questions and welcome queries from our my other co-presenters.
So we can take any questions right now.
If any of the in-house presenter, in-house participants have any questions?
So, taking off in about STP and the domestic usage. Did you explore about different treatment plant also like ETPs? Where like government is having norms of
Online audience will also.
yes. So like let me start the question again. So you have already discussed about STPs, right? And also about some domestic uses, right? Did you also check about effluent treatment plant? Like what Indian government has done for textile, they have brought out some norms of zero liquid discharge, right? Where you treat the effluent first, and then you process through some ME evaporator. Then you just like try to close it down by like with some hazardous waste or some salts also, right? So did you explore that one also, like and how AI can help there, right? That is one question, and I'm having another question also, like what like CPCB has done, Central Pollution Control Board. So once whenever you are trying to discharge the effluent, right, in any of the sewage, right, then there is a monitoring system. From there they feed the data to the Central Pollution Control Board on live, like you have to tell them COD, BOD, pH, everything, like how much TSS is in the effluent and everything, right? So can we use those kind of data and AI to leverage something for the industry?
To answer the first part of your question, um, I have not, as part of my research or my group's research, we have not looked at effluent treatment plants, uh, CETP or combined effluent treatment plants or industrial wastewater treatment plants. But of course, there are a lot of uses of AI in just maybe predicting the quality of the effluent that comes out from the treatment plant and so on. But that is not something that I focus on. I mean, there's plenty of research with AI applications on that. And to answer the second part of your question, so yes, CPCB has several mandates on how wastewater treatment plants or sewage treatment plants should perform, and although it is also a little hard to find, once again, consolidated long term databases where you have information on how all of the treatment plants across the country, for example, are performing. So for since I'm from Uttarakhand, one of the things that I do for my research is I refer to the Uttarakhand State Pollution Control Board website, and there is a certain amount of data available there. I'm not really aware of what other states are doing, but we do lack a consolidated, countrywide database. So once again, that might be something where AI comes in on how to fill in gaps, how to build these databases, how to make them more accessible through visualization portals and such.
Bihu,
Also
I
about
will,
STP water, right? Like
Bihu,
everyone is trying to like clean that STP water in a way, like output of the STPs, so that anyone can drink it, right? But I think the best application would be like the order, right? There isn't any fixed norm for the order of the water, right? And also the technology from which we can sense the order of the water, like a smell of the water, right? We don't get that one, and there isn't a norm existing, right? So we can use that one for agriculture purpose, right? So that might be a useful loop, at least for India. That's what I'm telling.
Yeah, so in India we are not really looking at portable use as something that's mandated by the government, at least short term. That's not happening. There are, like I mentioned, a lot of psychological barriers to the use of treated wastewater for drinking. But it's not just odor. The water is tested on several quality parameters, and then it is decided what should be done with that water. And one of the things that we do is either release it to the water bodies, and agriculture, in fact, agriculture use can be done with limited amount of wastewater treatment as well. So you don't need to treat it to absolutely those high standards before you use it for agriculture, because wastewater contains certain nutrients which are useful for plant growth. So we try to harvest nutrients from there as well. If any of my co-authors would like to add anything here.
yeah, Bihu, I would like to actually mention. Can you hear me?
Yes, yes.
Yeah, I would like to actually mention about CPCB, the question which was asked about the data and the sharing. Okay. I would like to actually say that the data, there is non existent data sharing. Okay. In fact, if you have used the platforms of CPCB at all in any serious way, you will find that it is actually woefully inadequate for any data sharing. I have been checking it out since at least 2014, which is 8 years. Okay, the thing it's not a train reservation system that you log in and then you look at the data and you do something. Okay, you're not booking a flight. The best way to share data is by a API. Okay, so in fact I'm trying to make some very critical comments here, but the fact remains that they don't even have a means, uh, whatever, even a state, forget the state of the art, even a commonplace thing which you see on a web portal which uses APIs to fetch data and make it available, right? And then you can actually have a key and you can share it. The best data sharing protocols, they are at data.gov.in, which is the Indian government's open data platform. Okay, CPCB is in actually even decades behind that in the data sharing. So they don't even have a practically working system where you can have data. Data sharing is actually very poor in all government sectors. I can say even in the US, we talked about USGS, and which is actually very top at the federal level. But if you start working at any area, like I've been working in Florida, in Orlando area, and other places, the fact remains that to get long-term data of your particular region, people have to build their own platforms. Okay, because because there is not never enough data at the right sampling rate that you want for your region. So I'm trying to say two things. Number one, we need better data sharing platforms. They are not adequate. The second thing which I'm trying to say is that for the location or the focus that we want, right, for higher granularity, chances are we'll have to create our own data set. But if we do that, we ourselves should actually have better data sharing platforms. So in the Blue Water, we actually made APIs and we made it available. So people can check that out. But I would encourage others also, and I'm very happy that Manav is making the data shareable. I would encourage people to use APIs to actually share data, not put login portals and all that nonsense, because you are not selling thing. Because if you are selling, then you will you that's not for data. You sell insights, you don't sell data. No one will buy that, at least in the water area. Thanks.
Yes.
So thank you for that wonderful session. Because I'm a who works on the water domain. My name is Ashwati. I come from Amrita University, and I'm part of a team where my background is computational social science, and I work with the social scientists and experts and social workers. So there are projects in which we work in the rural communities of India, where we deal with the water problems that they face and all. So from the presentation that you gave, two thoughts came into my mind. One aspect that you talked about was policy, and another was the impact of AI or data science in it. So there is two questions that came to my mind. From your experience, it will be like I would like to hear about it. The first thing is, when we talk about water quality, there is always two aspects. One, you mentioned context specific, so it could be temporal and it could be spatial also. The location where it is. So if there is a flood in the next 2 3 years, that might affect the whole water for the upcoming years, and the season might impact. One season they might have good water, another season may not. So the water that we offer, information that we often get is from different time for this same community or the same how discrepancies in the available terms of granularity, also the time and the context specific. Then other thing is from my experience, even if we have the research or the insights that we get from the data, often it is quite difficult to make people understand about it. Particularly when we talk about 70% of our population is from rural communities. So it is very difficult to make them understand why do we should be careful about water, what is its impact. So do you think it is more a problem of data sharing or knowledge dissemination, or is it lacking of the research, where is the imbalance?
Okay, so I'll take your questions one by one. To answer the first question, it would be good to have that kind of an ecosystem where we can take into account the fact that a water body might have just been flooded a couple of days or weeks prior, and study its water quality as such. The honest truth is that does not happen. When we talk about regulations, like I mentioned in one of my slides, the places where regulations come in are very specific. When you're drinking the water, what is the quality of the water? Of course, there are regulations for what the surface water quality should be like. So if you have a lake or a pond or a river, what should the quality be like? And there, these kinds of considerations do not come in. If you're drinking water, you want it to be of a certain quality that is set. And if you are a wastewater treatment plant discharging water into a water body, the parameters are set there. Now, having said that, that is the situation in India. In US, for example, they have a very different kind of a system for wastewater treatment. Depending on what kind of a water body you are discharging into, your regulations would be different. So if you are discharging into, let's say, a very sensitive water body, where there are very specific types of aquatic species which are sensitive to slight changes in maybe pH or water quality, you would want a different standard or a different level of treatment. If you are discharging to another water body where these kinds of considerations or constraints are not there, the regulations are different. So this type of what we call water quality based effluent limits, these are something that we see in the US, not so much in India. But it is very important to take into consideration at least the water body, or the use for which your water what you are using your treated wastewater for. So for example, he mentioned agriculture. If you're going to use it for agriculture, you might not need to treat it to the standard to which you would if you were maybe discharging into the upper reaches of Ganga, where you do find a lot of sensitive aquatic species. So of course there are a lot of subjective considerations that should come in. Once again, to drive those kinds of considerations, you need good databases, because it's kind of a feedback loop. If you don't have one, you can't get to the other. So I think I wouldn't say a lack of research per se, but I would definitely say that a lot of the research is handicapped because you don't have the supporting resources, mainly data. That's one of the barriers even I face in my work. And coming to the second part of your question, I think science communication is something that we all should work on. We the work that we do, we try to keep and a very elite audience in mind when we are writing papers and stuff. But I think we also need to keep in mind that for applications like water, the end user is the common man, and we need to figure out what their problems are and try and incorporate that in a better way. So that would be my point of view. I would like to ask my co-authors to maybe chip in on this.
So, Bihu, I will just like to add one more thing, and I agree with everything that you said. Is that in communication, one of the things which I found very useful is telling people about alternatives. So, if I tell you the air is bad, right, and the air is very bad, and the air is very bad, you won't stop breathing. So you'll just shut me, okay, because there's no alternative. But in the water area, you actually can have alternative. So I was actually interviewing some farmer who was actually growing vegetable in the in the Hindon Canal river, and he kind of said that if I know that the water is bad, I'm actually I am irrigating vegetables and I sell them. If I know the water is bad, I will actually use the groundwater or some other water because I want to get higher money, right, from my crops, from my vegetables I sell. So people are aware of quality and they are aware of their health. Everyone wants to do that better. That has nothing to do with education. Where we fail is our in communication is rarely about alternatives. Do's A versus B, right? So we should work on a communication, but we should also work on communication which gives people choices.
Sure.
Thank you. Yeah, yeah,
Yeah,
yes.
we can hear.
Thanks for the talk. It was interesting. I have a few questions. So, what about the trustworthiness of the data that we collect from the citizen? Because people may not have proper education that how they have to give the data, or sometimes it may not be reliable. Right? So, how do we ensure that the data is reliable and also it is true? Because it impacts the quality of the research that we do, right? In terms of the analytics.
Yeah, definitely. I think data collected from citizens is always a tricky issue. I would
Uh,
ask Manavendra to please chip in and
so I just wanted to know how do you deal with that and
yeah,
kind
yeah,
of
sure.
that.
I think
Yes.
he would be able to shed light on what they do. Yeah,
I can.
Manavendra, you are not visible or audible.
So while Manvendra is waiting, I'll just mention the thing which we did in our Neerbandhu application. And Manvendra, as soon as you join, please cut me off, okay? I'm just trying to not. Yeah, please.
Yeah, we can't hear you still. We can't even see you actually.
Yeah. So in Neerbandhu, what we did was we actually used data from physical sensor to cross-verify uh, the input coming from the human. Okay. The other thing is because it's a mobile sensor, like the location and time, the person cannot change. So you try to rely on some things which the person cannot change and rely on. Manvin, over to you.
We can't hear you. We can see you now.
How about now?
Yes.
Am I audible?
Yes. Oh, sorry, we lost you again.
Okay.
Yes.
Right.
Yes.
I'm audible now. Sorry, I don't know what happened. The settings kind of changed. So yes, so working with citizen science data is always challenging. So there are a couple of things that we have done in this particular application to make sure that the data is reliable. A is that we don't allow users to provide, the users can provide only one information every minute, which means a malicious user cannot really like put in like 50 different reports a minute and then kind of make the data set, you know, pollute the data set basically. So that's one thing we have done. Second thing is we don't allow the editing of the geolocation data. So you cannot, sitting in Delhi, you cannot really submit a data in Chennai, for example. So that also increases, at least the geolocation information is very reliable. And we always rely on the, I mean, the whole idea of citizen science is to rely on the wisdom of the masses. And the idea is that more people from one location provide the data, and then we correlate it with the satellite, whatever we are seeing from our simulation models and satellites, we correlate them to basically garner higher confidence in our results. So and again, there are a lot of other things we also look at, like device IDs and information that we collect to ensure that um, we don't get too much malicious data. We have also done one thing, is that we have kept no user information, because we kind of discussed this, like, should we have a user ID, should we have a login ID, which is true. Like if we have that, probably we will have greater, like more trustworthiness in the data set. But at the same time, it greatly reduces the number of people who are willing to provide us data. So we kind of chuck that one, and anybody can provide us data, and hopefully the validation and the reliability, we work on it in the back end. But overall, in citizen science in general, that remains a challenging issue. Yeah.
Yeah. So my next question is, what are the factors that you consider in the water, like pH level and etc.? So any
So there
idea?
are a set of quality parameters that we
Hmm.
look at. India government mandates certain quality parameters. If
Hmm.
you're looking at drinking water, it's going to be a certain set of parameters. Wastewater, something else. You can go to the CPHEO website
Okay.
to look at drinking water parameters, and you can go to the CPCB website to look at wastewater parameters.
I see. I see.
Yeah.
Okay. So my next question is like, did you ever look at the groundwater quality? I mean, so far you were talking about the I mean, the water which was polluted, the river and things like that. But what
Yeah.
about the quality of water in the groundwater? Have you ever thought about? I mean, looked into it?
Yeah, so there are people who work extensively in groundwater because it has its own mechanics, so it's
Okay.
very different. But once again, irrespective of where the water comes from, there are plenty of AI applications.
Mhm. Okay. So how frequent is this data collected?
Depends on the data set. So you might have daily, you might have monthly, you might have once in several years. Depends on the
Okay.
data set.
So, thank you.
Yeah.
So thanks everyone. So in the interest of time, I think we will close the session. But I guess you can talk to the speakers if they will be around. So let's give the speakers a big hand. Thank you. So thanks for the very informative session. Thank you.